So for everyone, this is the session on machine learning and AI applications and forecasting. If you're looking for the capacity market session, that's in the room right behind us. So I'd next like to introduce Dr. Justin Sharp from EPRI. Justin is actually the chair of our System Operation and Market Design Working Group. He finished a weather data set report with us about a year ago, and we're really excited to have him chairing the session. Justin?
Thanks, Debbie, for the kind introduction. I think most of what you're going to learn is going to come from the panelists, though. So this is the session on machine learning and artificial intelligence applications in forecasting. We have Sue Haupt and Karl, Critz, Jared Lee, and Andrew Akman, who are going to talk about various different topics today. We're going to kick it off with Sue, who's going to really give us an overview of AI and how it works and how it impacts power systems operations. In your guide right now, you have the second talk being Karl and then Jared. I'm going to reverse the order of those on the fly, and I know they're in the wrong order, Debbie, in the slides, but I'll figure it out. So without further ado, I'll let Sue kick us off.
And the remote is.
Do you want to walk around?
Not really. I'm here.
You can just use
I can use this. This works, but the remote clicker. There was one beat last session. We lost the remote clicker. It's not the end of the world, but.
There it is.
Thank you. Okay, so Justin asked me to do an overview of AI predictions. I'm going to talk about what is it, how does it work, what are the implications for power system applications. And many of us have been doing AI for a very long time. The low-hanging fruit was post-processing the numerical weather prediction results. We did a great job of that. Then we started building parameterizations based on machine learning. Again, that worked well. So in some cases, well, in almost all cases, it made them faster, and in some cases, it made them better. But I'm really going to focus on some of the newer applications, the foundational, the generative type models, and the impact that it's making on the meteorology community right now. So I'm tracing this initiative back to about 2018 and the European Center for Medium Range Weather Forecasting, ECMWF. You'll hear their name a lot. They are a leader in this. Two of their scientists, Peter Dubin and Peter Bauer, wrote a paper on how could you use AI in building a full model. And this is only 2018, 7 years ago, and they were doing toy models back then. And it was a toy neural net, and they built it, that it was equivalent to a, 21 degrees of freedom type weather model, and found that it could be competitive with those type of models on short lead times. Okay, and they showed some examples of how, if you do smart construction of these models, that it's even better. That really got things started. And the first talk I really heard on it was in January of 2021, an American Meteorological Society meeting where Dale Duran of University of Washington first presented these results about subseasonal scale forecasting using a large model. And what they did is they used deep learning, convolutional neural net to build an ensemble system for subseasonal to seasonal forecasting. We usually call that on the order of 4 to 6 weeks worth of forecasts. And the nice thing was that once it was built, they found that within 3 minutes, they could produce a 320 member ensemble of a 6-week forecast. And that ensemble produced similar metrics for a 4-week forecast as well as a 5 to 6 week forecast as the best European ensemble, which is considered the best in the world. And that really shook the community, a lot of, discussion around the community, and it really kicked the private sector into trying to build these machine learning weather models. So NVIDIA put out their forecast net, announcing it on Archive in February of 2022, followed by Huawei with Pangu Weather in November of 22. Microsoft followed with ClimeX in 2023, shortly followed by GraphCast, which is Google's model, just a month later. And then, more recently, Privy Weather in September of 2024. So all of a sudden, you have all these private companies, many of them working with university or laboratory colleagues, putting out these big weather models, each one claiming to be better than the last. Okay, so they each claim to be better, but it really takes a third party to verify it. And the ECMWF forecasters took it upon themselves to start verifying some of these models. So this is from a blog in June of 2023, really asking that Pangu Weather claims to be good. They made their code open source. We're going to run it against our best model of a similar resolution, or actually higher resolution. And they found that the headline scores do hold up to independent evaluation. And when they look even at some of the things that are most difficult to predict, like this is hurricane track position, that they can be optimized. And you can see in this case, it's within the uncertainty of whether Pangu Weather or their high resolution physical model was better. And so that really got people excited. But does it know the dynamics? And it's been almost 2 years now since Greg Hakem, together with one of his students, asked that question. And again, because Pangu Weather is open source, that was the model of choice, they looked at various canonical cases, and I particularly like this one, where they put a tropical heating source in the model and look at the reaction. And I like this one because I tried doing this with a statistical learning model back early in my career and found that it was very hard to do, but one could do it. I really didn't think the machine learning models could. But you can see from the top with this source, it starts developing a wave train, and gee whiz, that's a Rossby wave that is generated, just what we would expect. Now, this is a simplistic solution that it has not seen before, but it learned the dynamics to know that the resulting behavior should be a Rossby wave train. So this paper concluded that the model encodes realistic physics in all experiments, and it could be used as a tool to test ideas before we even go to the expensive physics-based models. This is the paper that kind of changed my mind and said, yeah, it might have something going with it. Okay, so like I say, ECMWF, they hired a team of about 30 researchers to work on their own machine learning model. They have been running similar things to GraphCast, Pangu Weather for a while, but they also asked, what if we could train it from observation? So this was the first paper out about a year ago by McNally et al. And they took all their data assimilation satellite measurements. Most of them are polar orbiting, which is why you see the data in strips going around, and use those data, historical data, to train a model, and then validate it against surface layer winds. So the predicted winds are the top of the blue parts, the observed down as two different time frames there, and they're amazingly alike. And this is based solely on observations. Okay, and they threaten to be able to use their entire data assimilation stream to train later models, huge amounts of data. Okay, so Greg Haken is still asking great questions. We've come to the conclusion in the meteorological community that the limits of predictability are about 14 days, and that's been proven in multiple type scenarios, kind of looking at the convergence from, what we used to think, and kind of came up with about 14 days. But Greg and one of his students took GraphCast and found that they could get an average error reduction of 86% at a 10-day prediction, and the skill lasts as long as 30 days. We have traditionally thought that predictability goes away long before that. And their last statement here is, these results demonstrate that given accurate initial conditions, skillful deterministic forecasts are consistently achievable far beyond the 2 weeks that we have looked at before for limits of atmospheric predictability. Okay, so, everybody is pretty impressed with this. ECMWF has been running, what they call the AI forecast system. Their normal system is IFS. This is the AIFS, experimentally for well over a year, but, really back to 2 years when they were first doing those. But in February, they began to operationalize it. And, they here in this case, where they have tuned the AIFS, you see that it actually has better correlations out much longer, and the improvement is bigger the longer you go than their traditional model. They claim that it outperforms the state-of-the-art physics-based models for many measures, including difficult things like tropical cyclone tracks with gains of up to 20%. Again, totally surprising to the meteorological community. Okay, that's what's happening in Europe, but what about NOAA? Well, NOAA has been running some of these same open source models, Pangu Weather, GraphCast, ForecastNet, experimentally in the background. One of their labs based at CSU, experimentally for over a year now. And just last week, NOAA put out a press release that they're working on Project Eagle that will accelerate the AI weather prediction in the US as well. And this is a movie of wind predictions out of it. Eagle is going to be both they'll have a deterministic realization. They call it Global Eagle Solo. And there's also a Global Eagle Ensemble where they'll be running 31 global members. And they plan to do this operationally in the near future. Okay, now I sit at National Center for Atmospheric Research. We do a lot of research in machine learning, and some of my colleagues there have created the Community Research Earth Digital Intelligence Twin, CREDIT. CREDIT is a framework for deploying models like this. Since we're a research lab, everything there is going to be open source. And this framework has various components. One of the claims to fame here is that they added mass latent heat, moisture, and energy conservation schemes, and found that it really does improve it. So blending the physics with the machine learning. In addition, they found that, typically in these, one of the problems with these AI models is precipitation, partly because the AI models, it's hard to get the terrain-dependent precipitation rate. So they added terrain-following coordinates and found that it really did help precipitation forecasts. And then yet more recently, they released Camulator, which is a machine learning version of NCAR's global climate model, the atmospheric portion of that, with the intention of eventually coupling it to cryosphere, surface, and the other components of Earth system models in the future. Okay, so here's just a slide from David John Gagné on Credit, an open foundational platform for deploying AI weather models, brings in data sets not only from ERA 5, the ECMWF product, but also, community atmosphere model from NCAR, GFS from NOAA, CONUS 404, which is a 4-kilometer version. It builds various models. The first weather model is WeatherFormer. They brought in Fuji, which is, a European-based model, and working on a graph recurrent transformer. And again, some of what makes this different is it works to conserve mass, energy, and moisture with some improvements. Okay, so these are typically global models, but oftentimes, in the last session, we heard all about the HER, the high resolution rapid refresh. Can we emulate those storm scales as well? Well, the University of Oklahoma has been working on it as well. This is the final paper. They had an archive paper before March of this year, what they're calling Warn on Forecast Cast, where they're able to do severe storms very quickly. And then NVIDIA has recently announced their Stormcast. And again, it's a kilometer, several kilometers. That's convective scale, able to get the updrafts modeled, actually simulated correctly rather than modeled. NCAR is also working on a mesoscale digital twin. Ethan Gutman, a colleague of mine, has taken that CONUS 404 data set, 4-kilometer, both current and future climate, and then adding a UNet to get the time dependence in there. A team that I'm working with is taking, the mesoscale, downscaling into the urban scale based on fast eddy simulations. That's our GPU-enabled large eddy simulation code. Goes down to 5 meters we're using to train urban scale modeling. And then we'll be adding a neural operator to get the time dependence at those scales. Okay, so the idea is to bring this all together, take that global model, be able to use generative methods to downscale to the mesoscale, and then also downscale from mesoscale into these large eddy simulation scales. So in summary, machine learning has become a necessary component of modern weather forecasting. It's doing well. There's some explanations on why it's doing well. It's revolutionizing weather prediction. It's really all happened in the last 5 years or so. It's very new. We need to understand the full picture. There's still places for hallucination. Adding the physics is helping to avoid that, but the prospect for the future is really quite bright in this realm. So thank you.
Thank you very much, Sue. I'm going to quickly move to the right slides here. Is that it? Perfect. And introduce Jared, who is also from NCAR, and his talk actually kind of follows up directly on some of the things that Sue was talking about, the comparison of AI weather predictions to traditional NWP.
Yeah, thanks, Sue, for kind of setting me up here. So I give the subtitle of my talk, How Good is AIFS Really? It's pretty good, but so Sue also showed the same chart in her talk. So as we know, there have been a lot of developments lately, but generally a lot of the claims that AI models have been outperforming physics-based NWP models. It's on root mean square error, it's on anomaly correlation coefficients of the 500 hectopascal geopotential height, so about 5-6 kilometers up in the atmosphere. And a lot of this training is based on historical data sets, especially the ERA 5 reanalysis from ECMWF. And so we just have questions about how are these verifications being done? Are they robust? And so just kind of looking at what AIFS produces. So it produces, there's some details here about what their machine learning approach is here, but I won't dwell on that too much. But the AIFS, it produces a bunch of different fields: geopotential, horizontal and vertical wind components, specific humidity and temperature at the mandatory pressure levels up through the atmosphere, but several surface level variables, including pressure, 2-meter temperature, 2-meter dew point, 10-meter winds, and then also some information about precipitation as well. So what AIFS does is it's able to handle high resolution input data really efficiently and supports parallelism for scalable training. Right now, what it does is it produces forecasts at 6 hourly output, and it receives as input a representation of either ERA 5 or actually the ECMW, right now the ECMWF operational analysis at 6 hours past, and then the current time, and then it forecasts the state at 6-hour intervals moving forward. So it was trained on ERA 5 up through 2018 and now uses the ECMWF operational analysis. So the technology within AIFS, it is similar to Google's GraphCast. So the input states, they're defined on a high resolution lat-long pressure level grid. GraphCast then predicts the next state of the weather as the lat-long pressure level grid. And then the forecast is made iteratively by applying GraphCast to the previous predicted states, which then produces a sequence of states to represent the weather at the lead times all in a row. So as Sue laid out, there has been a lot of progress in AI forecasting models, from 2019 up through 2023. Just every few months, there was another, or a couple months, there was another paper coming out showing just the massive improvement over a couple months before from the prior model. So AI models were getting better and better quite rapidly, and this was getting people very excited and still has people excited. But over the last couple of years, a lot of that improvement has really leveled off. So we're no longer on this trend where AI is going to take over the world. Now we're maybe being a little more realistic about what AI can do and some of the potential limitations that there still are. And so as we've shown with, there have been a lot of experiments with DA and ensembles showing that there are physical inconsistencies and instabilities in the model. And so we need to engage with actual data and model physics. And some of these AI models still blow up, they go unstable. And so we need to understand better what are the situations in which the AI models are doing well, where are the limitations, and so that we just have a right-sized interpretation and understanding of what it can do. So we have a small internally funded project at MSF-NCAR to compare the AIFS to 3 physics-based NWP systems: the IFS, the GFS, and the HER. So the IFS, GFS, and AIFS, they're all, well, I guess the GFS and AIFS are both 1/4 degree grid spacing. The IFS is at 9 kilometer, and then the CONUS, or the HER, sorry, is at 3 kilometer grid spacing. So we really want to see are there advantages to a high resolution model like the HER, or can the AIFS at its coarse grid spacing, can it beat such high resolution models and a couple of leading global models too? So we're limiting our study to CONUS, and these 2 maps show the observations from the ASOS and the AWOS networks. So for those of you who aren't aware, they're the standard surface weather observing networks, generally at airports across the US, that are operated by NOAA, FAA, and various state agencies. They measure 2-meter temperature, dew point, 10-meter wind speed and direction, visibility, pressure, precipitation, and sky conditions. And here we're just going to look at the 2-meter temperature, dew point, 10-meter winds, and the pressure. We're not dealing yet with precipitation or visibility or anything like that just yet. So these two maps, the top is for temperature and the bottom is for 10-meter winds. It basically just shows where the stations are and how frequently they reported. The ones that are yellows and greens have high availability. And then there are a few stations that had a few reports during the period, during the 1-year period. So that just gives an idea of how frequent the various observations are. Okay, so over the next, I'm going to just spend a minute orienting you to these charts. So these are getting into some results. So what we're doing is looking at forecasts from that were initialized from March 1st of 2024 up through the end of February 2025. So this is 1 year of forecasts initialized at 0 UTC over CONUS. So, and we're looking at the every 6 hours. So we're putting everything on an equal footing. So we're taking just the forecast output from every 6 hours from each of these models, even if they themselves had a higher temporal resolution. So on all these charts, all these plots, the color code stays the same. Yellow is GFS, purple is HER, green is IFS, and then blue is AIFS. And we have 3 groupings of statistics. We have the root mean square error, the mean absolute error, and then down here, the mean bias error. So for sea level pressure, we again see blue for AIFS. AIFS is doing really well, and by about 5 days or so, it's consistently beating the IFS. I'll note that the IFS time series stops here at 240 hours because partway, a few months into this 1-year simulation, then we started getting 15 days of IFS forecast. And so at first we saw a huge jump in the error for the IFS, which looked a little strange. So we just cut it off at 10 days for now. But that also does show that there's a huge difference in the seasonal statistics of validating these models, which I won't get into today. But we can see for the sea level pressure, actually the HER is doing more poorly than the 3 global models, and that's mainly due to a fairly large negative bias in the sea level pressure. The image on the right is it's the same as the left, is just zooming into the first 48 hours, the first 2 days, so that we can see that. So a little more relevant to energy. Now this is the 10-meter wind speed. I'll get into the 100-meter wind speed a little bit later. But for 10-meter wind speed, here's where we see the HER actually doing quite a bit better, especially over the first day or so. So HER is this purple line, and so because the HER is at a 3-kilometer model, it's resolving a lot of the terrain, whereas the AIFS is at 1/4 degree or about 31 kilometers. It's not resolving the terrain as well. So this shows, again, it depends on what is your forecast question. What do you care about for whether the AI models are truly doing a good job? And interestingly here, that we do see a strong diurnal pattern in the errors of for 10-meter wind. But for HER, this diurnal pattern, HER and GFS, this diurnal pattern is much more muted compared to both the IFS and AIFS, which have large diurnal swings in the error for 10-meter wind. But then once you get out beyond a few days, then the AIFS is performing the best, at least in this bulk error statistic. We see a similar story for 2-meter temperature, where in the first 6 to 12, arguably 18 to 24 hours, HER is doing really well, and then AIFS takes over. AIFS is, for 2-meter temperature, is really honestly blowing the other models away. Again, in this bulk error statistics sense, with the smallest bias. GFS here has a very large diurnal bias in the 2-meter temperature in particular. But again, we see for the high resolution models in the very short range, we do see benefit from still using HER. So we're wondering also, in a lot of these comparisons that we've seen, it's pretty common to say, oh, the AI model is beating an NWP model, but they often use the raw NWP model forecast, whereas artificial intelligence models, with the training for the AI models, it's usually doing some sort of implicit bias correction. So what I was really interested in doing is trying to answer, well, if we do a bias correction or apply at least a simple bias correction, that should at least be closer to an apples to apples comparison, so that the standard NWP models are also having some of that bias taken out. So by looking at Taylor diagrams over the first 48 hours, we're looking at standard deviation, correlation, and the centered root mean square error. So that's removing it's basically doing an inherent simple bias correction here. And for 10-meter wind, which is on the left, 2-meter temperature on the right, we see that the HER model is showing higher variability than the AIFS model is showing. And I'll show this also in some time series plots a little later. Basically, what we're seeing is the HER model is matching the ups and downs of the observed wind speed much better, getting the diurnal swings in that, whereas the AIFS is a much smoother forecast because it's lower resolution. It's not capturing the terrain. And so that's what we're seeing here in this Taylor diagram. And for the 2-meter temperature, all the models are clustered pretty closely together, but AIFS and HER are pretty much neck and neck over this first 48 hours. So again, we care about the energy here at this conference. So starting February 25th of this year, when the AIFS went operational, they started putting out forecasts for 100-meter wind speed and also solar irradiance. We're not looking at the solar irradiance here because the solar irradiance is a 6-hour accumulated GHI value, which is not terribly useful for energy applications, at least not yet. So for this talk, we just started looking at the 100-meter wind speed. But as you all know, there aren't, unlike for the surface, where we have stations all over the US with publicly available data, we do not have a similar network for 100-meter wind speed. While there are nacelles available, or while there are nacelles with anemometers all across the country, that data is not publicly available. They're generally not tall towers. You know, we could get some spotty observations here or there from LIDARs and things like that. But for now, we're doing our validation against the ERA 5 100-meter wind speed. And showing this Taylor diagram again here, AIFS is performing the best, because the best performance is to match the observations, which is this black star down here. However, again, recall, AIFS was trained on ERA 5 up through 2018. And so ERA 5, often in the power systems community, and Justin has talked about this in his report too, and I've seen this at other conferences, including AEMO which was just in Italy a couple of weeks ago. It's very common to treat ERA 5 as the truth, as what actually happened. But ERA 5 is based on a model as well, and like any model, ERA 5 also has its own biases and errors, and those need to be accounted for. So AIFS for 100-meter wind speed is doing best when compared against ERA 5. That shouldn't be surprising. Basically, AIFS in its training learned the biases that ERA 5 has. And this shows that in this comparison that HER is the worst performing model. But is it actually the worst performing model? What we know for sure is that HER, again, 3-kilometer grid spacing, has a lot of events in it with a very high spatial resolution that the AIFS or the ERA 5 is just not representing at all. So we can't actually conclude from this that the HER is bad and the AIFS is good for 100-meter wind speed. We need to compare against observations, but we also don't have enough observations to do a robust validation. So I just say this as like, be wary of claims that AI is solving the world. AI is solving the problems that it was trained on, that it was trained to do, which is to optimize often root mean square error over the bulk. But we need to ask the right questions for how well is it doing. And so looking at a couple of time series, so these are just some random days. So starting March 1st of 2025, March 2nd of 2025, the top left is for Denver International Airport, and the lower right is for Copper Mountain. So we picked a couple of sites with that had terrain where we thought the AIFS might struggle a bit and the HER might do well. And for 10-meter wind speed, lo and behold, we see the HER, which is purple again, generally over the first 48 hours, generally doing a good job of matching the observed variability in the 10-meter wind speed. Whereas the AIFS just happily goes along, is generally not representing the actual observed variability in the winds. And this is even more pronounced up at Copper Mountain. We see this purple dash line, it's doing a really good job following the observations, which are in black, sometimes with a little bit of a time lag. But the AIFS is just producing, it's just not representing the daily swings in the observed wind speed. So AIFS is struggling in high terrain, which again, we'd expect. So in conclusion, AI-based models are showing strong potential and can outperform traditional NWP models in many global metrics. AIFS does offer rapid and energy efficient forecasts, but currently with lower resolution and more limited lead times compared to the IFS high resolution ensemble. HER remains superior for short range and high resolution forecasts, especially for surface variables like wind speed. But even after a simple bias correction, AIFS is not outperforming other models here. So more improvements are needed for handling physical consistency, ensemble generation, and also regional and local scale performance. DA and hybrid forecasting approaches might be able to bridge the gap here between physics-based and AI-based forecasting. And like I mentioned before, AIFS is producing solar radiance as a 6-hour accumulated GHI, but that's not yet suitable for most solar energy forecasting applications. So it's not, they'll get there, but we weren't able to evaluate that just yet. So we're still doing this. So we'll add more months to our validation as 2025 rolls along. We want to look at regional validation, not just CONUS-wide. We want to look at seasonal validation, not just the whole period. We also want to look at how is AIFS doing in different parts of the variable distributions? How is it getting more the tails of the wind speed distribution, for instance, rather than just looking at a bulk validation. We also want to look at how is it doing spatially. We want to validate the 100-meter wind speed against other analyses too, not just the ERA5. And also one of our collaborators in Italy, he'll be doing the same performance evaluation over Italy so that we see how it does, not just in the US. And I will stop there.
So next up, we have Karl Critz, who is going to, oh shoot, I think I fouled that up big time, who's going to talk to us about using AI for subseasonal to seasonal forecasting. Is that the right starting point?
It's close.
All right. Hi, Karl.
Test. All right. Hi, Karl, Salient Predictions. We produce a long-range 100 to 365-day probabilistic AI-based weather forecast. And what we're going to be here to talk about is specifically the issue of reliability. Reliability has a specific mathematical meaning and definition, and that's one of the big differentiators between numeric weather prediction and AI weather forecast. What we're going to do is take reliability and show some real-world results with dollars attached to them, because that's ultimately what people care about. So that's where we're going. What we're going to do is start off with where we started when we began our AI journey, which is we started producing all of these reliability plots. And that's one of the big differences between AI and NWP is in AI on the left here, when the AI model says something is going to happen 60% of the time, then ideally it does happen 60% of the time. That means you have a reliable, well-calibrated model. One of the ways that numeric weather prediction tends to struggle is in that calibration. So if your model says it's going to happen 60% of the time, it actually only happens about 40% of the time. And the reason for that is that the way you get ensemble variation with numerical weather prediction is you perturb the inputs and then you spin the simulation out. But you don't really know how you should perturb the inputs, which means that very often you end up over predicting. You're overconfident. So we started showing these sorts of graphs to our customers, along with other abstract statistical measures like continuous rank probability scores, some of the other scores you're seeing like RMSE. And people just kind of shrug and go, well, that's great, but why should I care? What impact does this actually have on my life? So what we're going to do instead is we're going to take this through a decision-making framework and then we can backtest that against commodity trades in order to say, well, here's what it actually means if you are using it to make decisions. But first, if you'll indulge me in a little detour, in terms of understanding decision-making theory, we're going to leave weather for a second and talk about markets. So this guy, Robert Prechter, he's awesome. Over the course of his career, he predicted every single bear market that ever happened during his career. Very proud of that. You'll even see he's got a crystal ball on his desk. So that's great. He's got 100% recall. He's got a dirty secret, though. Maybe you're able to guess it, which is basically every time he published a quarterly newsletter, he said there's going to be a market downturn. So though he has perfect recall, his precision is terrible. And what that means is his predictions are basically unusable, because if you ask the question, did you predict event X? Sure, great, he's got great performance. But if you ask the question, when you say event X is going to happen, how often does it happen? If it never happens, you're crying wolf all the time. And that's not very useful to make decisions based off of. So we're going to be looking at the difference between recall, which is this, and precision, which is this, and compare how these two different forecast methodologies compare. So what we're going to be looking at here is the Salient GEM model. This is a generative AI model. It's a little different from some of the other AI models you've seen in that it is a two-stage process. We start by doing a principal component analysis that really breaks down the major meteorological modes, but those are kind of blurry. So then from there, then we add in some of the additional fine grain detail using diffusion, which is more where GraphCast and other AI weather predictions start, is by using that diffusion methodology. And what this does is it means that the meteorological modes are guiding the diffusion, so it's less likely to break down, less likely to hallucinate, and then also has the advantage of being really cheap to run. So we spool this out to 100 days to give you some nice long-range forecasts. We also generate 200 ensemble members, so you get a better idea of what the variability is happening. But for this particular investigation, we're just going to look at 14 days out into the future. We're going to look at California, and we're going to look at 3 different price hubs, and we're going to look at trying to identify a 95th percentile hot day on the theory that market prices are often driven by that. And then by identifying those hot days, we'll trade on those hot days, and then we'll backtest how well did your trades end up netting you some value. So this is where we're going. You don't have to understand this yet. We'll walk through this step by step, but ultimately we're going to calculate an ROI value based off decisions from these forecasts. So let's start just looking at how these forecasts operate. This is an example of EC ONS being overconfident, where EC ONS is that orange band, and what you see is that it's high. So if we're trying to identify days that are above a certain threshold, in this case, it's about 35 degrees C, you see that, yeah, most of the EC ONS is above that threshold. So you kind of blur your eyes and go, yeah, EC ONS is probably saying it's going to be extreme. The gem forecast in the blue is well below that threshold and much closer to the black line, which is this is what actually happened. So the salient gem forecast, much closer to what actually happened. So this is one of these examples where the other forecast didn't do a great job at identifying extreme. It said there's going to be an extreme. But what we need to do is we need to take all these complex probabilistic forecasts and we need to compress it all the way down to a single true false. Does your model say it's actually going to be extreme? So we're going to have this process by which we look at the number of ensembles on any given day that are above your extreme threshold. That's the probability. Then we're going to come up with we're going to optimize a decision-making threshold where we figure out how many of those ensembles are above above that target in order to try to optimize that precision and recall balance. And then if you're above that threshold, then your forecast has said you are extreme. You say yes, you take an action on that, and once you have that, then you can back test that against markets. So this is an example of what those decision thresholds look like. So you'll see that in general, the EC-ONS has a much higher decision-making threshold, and that's because of the overconfidence. Because so often it's saying, yeah, it's going to be extreme. Yeah, it's going to be extreme. You set your decision-making threshold higher in order to try to optimize that precision recall balance. Salient forecast, on the other hand, has a much lower decision-making threshold. It's much more sensitive. And what that means is that in this case, even with that high threshold, the ONS forecast is giving you 10 days that it says are extreme. The Salient forecast does have two false positives out there in days 11 and 12, where it did cross the decision-making threshold, but the AI forecast is much less likely to cry wolf and give you that false positive. Now, when we want to actually find things that really exist, this is a case where we really did have 2 days of observed temperature that were above that threshold or above that target. And we want to ask ourselves, did these two forecasts correctly identify that? And what we see is that because of that very, very high decision-making threshold, even though these two forecasts end up looking very similar, they kind of track right on top of each other. The EC-ONS forecast didn't hit its decision-making threshold and it missed. So this is a negative where the EC-ONS said, nah, we really need a lot of evidence before we truly believe this is going to be extreme. Didn't flag it as extreme, and we have a lack of recall. Salient Gem, the AI forecast, it was above its decision-making threshold. We properly identified 2 hits. So now we have a decision-making process by which we say whether or not your forecast identified an extreme. And what we can do then is we can break that into a 2x2 confusion matrix where it's on the y-axis, whether or not your forecast said there was going to be extreme, and in the x-axis, it's whether or not there was an extreme. So if your forecast said it was extreme and there was an extreme, it's a hit. If your forecast said it was going to be extreme and no extreme happened, that's a false alarm. So by using these, we can now look at how well did these forecasts perform when we're making decisions. So to start by looking at recall, we can see that the AI forecast did a little better on recall than the numeric weather prediction. So we have a little, like a 68% recall versus 64% recall. I'm not saying this is hugely significant, but it's there. It's a nice little bonus. The really big difference happens at the false alarm level. So the false alarms you're getting out of numeric weather prediction, you're getting 13% of the time you're false alarming versus 10% of the time. And what that means is you're getting almost 200 more false alarms per year as a result of these greater degrees of that crying wolf. No, this is great. You can decompose these into what we call an F-score that balances, that's the harmonic mean of precision and recall. But we found that nobody cares about F-scores. What they do care about is dollars. So what we can do is we can back simulate what happens if you say, all right, anytime my forecast says there's going to be extreme going out into the future, I'm going to buy an option to, I'm going to buy an option for that day in the future on the assumption the price is probably going to go up. And then you can look at the delta between your purchase price and the sale price. And then what you can see is that when the forecast fizzles, you lose money. So you made the wrong call. Sorry, you shouldn't have bought that option. When the forecast is right and there is an extreme, you make money. Great. But one of the really interesting things about the AI forecasts is that when they're wrong, they tend to be wrong, but it's a close miss. And what that means is that you get kind of like a happy miss, where even though you did the wrong thing, because of the scattered relationship between price and temperature, you kind of got lucky and you didn't actually lose that much money overall as a result of following that false alarm. On the other hand, when the numeric weather prediction is wrong, it's wrong, much more likely to be wrong big. And as a result, you don't get any of those happy misses. So you lose more off of the false alarm. So there are three effects then of you get out of the AI, you get greater recall, greater precision, and also when you're wrong, you don't lose as much. All these same things also happen with EC-ONS. So you're seeing some of that greater precision, greater recall, and then also a greater value coming out of those trades that you're making. And so in the end, off of the AI forecast, you're getting a higher ROI in general than you are off of the numeric weather prediction. So this shows you some of the about what reliability really means in dollar value for making those decisions. But we're not done yet, because you can go one step further. And now you can use the deltas between the two forecasts. So now what we're going to do is we're going to have a 2x2 strategy where we look at how what are the two forecasts saying relative to each other on any given day. So let's say the AI is saying it's going to be extreme and your NWP model says it's going to be extreme. You're going to go along just like you did before. Same strategy as in the single paired strat, or the single forecast strategy. Same thing happens when both forecasts say that you're going to have normal. You just don't do anything. You don't buy. The really interesting thing happens in the off axes, where if the AI forecast says there's going to be extreme, but the NWP says it's not, you now have unique market information that other people don't necessarily have. So we're going to increase our order size. We're going to double down. And then in the other situation where the numeric weather prediction says there's going to be extreme and your AI weather prediction says it's going to be normal, you're going to bet that, in fact, that extreme isn't going to happen. So you're going to short the market and you're going to act against what everybody else is doing. So what we can do, we can break that down into that confusion table. Now it's kind of a 2x2x2 confusion table, but we'll expand out each of those forecasts on the y-axis and then what actually happened on the x-axis. And what we see is some really interesting things. So on the back test, one of the really interesting things is on that short happens a lot. So 5% of the time, the AI forecast is saying things are going to be normal. The NWP is saying it's going to be extreme. The market's probably chasing a phantom. You're working against the market, and that short pays off quite nicely when you are working against the market, and gives you the opportunity to generate some revenue in a case where you otherwise weren't, because you were just saying, it's going to be normal. I'm not going to do anything. Now, all the time, it's normal, and now you actually have an opportunity to make some revenue there. One of the other really interesting things we're seeing here, and this is related to earlier, that idea of the near miss, is in the case where AI is saying it's going to be extreme and the numerical weather prediction says it's not, your expected value of the trade is actually quite positive. So it's not as great as if the weather event hits, but it's actually kind of a no-lose scenario. Like in both cases, your expected value is coming out higher as a result of making these of this double down trade. So we have two new ways to generate revenue off of this paired forecast strategy. So you've got when you're doing the double down, you can actually take advantage of those happy accidents, and then you've also got the shorting to take advantage of the extreme that doesn't end up happening. All those things also happen with EC aunts. So you're getting the same thing with the happy misses as well as the revenue generated out of shorts. So between these two, now what we see when we are looking at the paired strategy is, in general, if you compare the NWP alone and then what you do, the trading strategy you get out of AI, you get a certain lift. But then the paired strategy actually gives you about double the value out of just using the AI. So now you've got that precision and recall, and you're using that to your advantage, not just for the singles for single forecasts, but actually looking at differences between those two forecasts. So what does this all mean in the end? Is traditional NWP, as represented here by gaps and aunts, is overconfident. It's not as reliable, tends to go off on wild goose chases, and can lead you to take action that you shouldn't. The AI models tend to be better calibrated, and what that means is that you are less likely to go off on those false those wild goose chases. And also means that you can notice when the market is overreacting, you can work against that. So you've got some alpha, you have information the rest of the market doesn't, and you can use that to your advantage in your decision-making framework. So, and then I just want to say, this may sound like a bit of a commercial for the Salient forecast. A lot of the other AI forecasts have this same property of reliability. And that really just comes down to that fundamental difference between numeric weather prediction, which is hard to calibrate and perturb your inputs properly, and AI, which is just natively, because it's training to the dispersion of the model, it gets that dispersion right. So it's neither over or under dispersive. It's getting that probability distribution right. And you can use that to your advantage in making your decisions, be it for trading or operations or agricultural commodities if you want. Thank you.
All right. So next up, we have Andrew Akman from AEMO in Australia, and he's going to chat with us about the use of machine learning in forecasting. And kind of moving back towards sort of some of the more traditional methods so that we're not throwing out the baby with the bathwater. Get to the right place. See it there? Keep going up. There you go.
Cool. Hey, everyone. I'm Andrew Akman. I'm a principal data scientist with the Australian Energy Market Operator, and I'm here to remind everyone to not forget about machine learning, forecasting beyond the AI buzz. So I just want to be really clear. This presentation is not intended to be resistant or antithetical to AI in any way. It's just that large language models seem to get a lot of the spotlight, and not blaming that. It's an incredibly profoundly world-changing kind of technology as we're all experiencing. But for many of us in this room who are very interested in forecasting, that scope and context goes beyond language-based models or language-based context. So I'm really here just to talk about real-world applications or things that have worked really effectively for us in the machine learning space. So today, I'm going to give a very lightweight introduction into AEMO and what we do in operational forecasting. I'm going to have one slide that's just going to talk about the AI umbrella, and I'm going to talk about our machine learning journey. So it's going to chart that journey through the lens of our demand forecasting system. Depending on how I go for time, I'll probably quickly get through kind of some new and emerging opportunities that are happening elsewhere in the machine learning AI space. So, AEMO and operational forecasting. So we are the Australian Energy Market Operator. We are an independent energy market and system operator. We have some gas functions that we do, but chiefly, particularly what I'm concerned with, is our two key electricity markets. That's our main East Coast market, as well as our West Coast market. That covers about 95% of the entire population. Within operational forecasting specifically, we are very much concerned with that really short to near-term forecasting. So that's everything from 5-minute ahead dispatch range, that intraday, day ahead kind of forecast horizon that's really critical for market efficiency as well. And we go as far out as that 1 day ahead operational planning kind of window. The main things that we do in operational forecasting is that we are responsible for all demand and rooftop PV forecasting. Every single wind and solar farm that's registered within our system, we are also responsible for forecasting the generation of all those. And we have a whole suite of other tools, uncertainty products, probabilistic packages, a lot more that we do, but our primary kind of systems that we kind of maintain and concerned with are here. Now, I'm going to be talking a bit more tomorrow about a lot of the trends and impacts that we're seeing, particularly when it comes to weather and rooftop. So I highly encourage people to attend that if they want to learn a bit more. But I really just wanted to put up this slide just to provide a bit of context as to why we are so interested in investing in more R&D into this space. So Australia has, I believe, the highest penetration of rooftop PV per capita than any other network or country in the world. Right now, I believe about 25% of all generation installed capacity is rooftop PV, which is all behind the meter. So that manifests itself in an incredibly dynamic way when we're trying to forecast our demand. So right now, about 28% of our operational demand is met by large-scale VRE, but we are in the midst of quite a tremendous energy transition. So what is happening here is that we are continuing to see more and more behind-the-meter entities and rooftop solar coming on the grid. Our operational demand itself is increasing and growing itself, and that's very much driven by population growth, electrification, a few other aspects. As our more traditional thermal fleet, which is mostly brown coal and black coal, is set to retire over the next few years, we're going to see that new generation sources emerge with wind and solar, and lots of new technologies coming on: batteries, EVs, demand responsive kind of behaviors, all of that. So the point is that we have a really big transition. Everything is evolving, and our job in operational forecasting itself is also evolving. So we are really interested in not only operating things today, but ensuring that we adopt the right strategies, technologies, and tools to ensure that we can continue operating efficiently today and into the grid of tomorrow. So the AI umbrella. Sometimes what's a little frustrating is that when people use the term AI, it becomes a bit synonymous with large language models, right? Like ChatGPT, Gemini, and all that. But the reality is that AI is much more of an umbrella term. It covers a diverse range of disciplines and technologies and has been around for many years. So machine learning, deep learning, robotics, large language models themselves, they all fall under this AI umbrella. So I do want to be clear that even though I'm just talking about machine learning and a bit of deep learning today, I'm still talking about AI. Everything we're talking about today in this panel is AI, and it's a lot more than just large language models. So let's get into our machine learning journey. So we're going to chart this through our demand forecasting spectrum. So that's the one use case that I'm going to focus on just to kind of chart the evolution there. Just a bit of context on our demand forecasting. When we have our load or our total demand, we're not really that interested. Sorry, we don't actually have that distinction of net load like a lot of other kind of US operators here use. So we are just really interested in total demand that needs to be met by generation. In some ways, on the demand side, we're kind of agnostic as to where the generation actually comes from. But when we do obviously look at the supply in order to actually reliably and efficiently meet that demand, we are very concerned about availability and as well as renewable forecasting and a lot of other things there. So our demand is mostly met from industrial, commercial, residential components. And then of course we have a big factor of distributed PV that's happening behind the meter that is impacting that. I will show some pretty interesting images and I'll show our duck curve and how that's evolving tomorrow as well. But really what I just want to say is that because we are ultimately responsible for the entire country, and it is a very big country, there is a lot of diversity there. So there isn't a one-size-fits-all solution. We constantly have to create systems and forecasting methodologies and strategies that kind of cover everything. And we are sometimes very focused in, but also try to make it robust and flexible enough that it can be applied to other places. So let's start our journey. This is our foundation, linear models and the power of simplicity. So at a really high level, this is our demand forecasting system. We've got a bunch of inputs here. So that's, weather data, our estimates of behind the meter rooftop PV, calendar information like type of day, recently observed data, etc. We take all that data, we put it into our demand forecasting system, and magically we get our operational demand. I think what's quite interesting and why I am kind of starting with this is that our primary market-facing forecast system is inherently just a linear regression model. And it works really well. It is incredibly effective. So for many years and still till today, that is our primary market-facing forecast model. And the value here isn't that it just works really well, but also it has all these characteristics that are very appealing. So simplicity, they're really straightforward to understand, and it also has a lot of transparency. So the predictions themselves are highly interpretable, and it allows us to kind of explain and communicate what is going on and what's driving certain outcomes of the forecast itself. But because we are relying on a third-party vendor system, and this preceded kind of my time with the organization, we lacked a bit of flexibility to rapidly expand our model suite or adapt to new challenges without significant overhead. So moving there, we decided to boost ahead and embrace open source, ensemble, and machine learning models. So as I mentioned, we had that need for more agility, more robust modeling toolkits. So we definitely decided to adopt more open source machine learning libraries through Python, through R, and this allowed us to build a richer, more diverse suite of models. More specifically, we lead heavily into boosted tree models. That's XGBoost, LightGBM, CapBoost. We use all three of those. These models, I'm not really going to describe the architecture of them or about them. It's not really the point here, but they are very, very effective at kind of understanding and kind of implicitly like learning relationships, particularly through very complex patterns. So really good for these sort of models. Now that we have these models, we can start communicating them and showing that to our analysts. This had a few different benefits. Firstly, machine learning models, they were really good. Now, our linear models already had a very high bar to me. They were highly accurate. Intention wasn't to try to blow it out of the water, but the machine learning models, on average, performed a little bit better. So that was fantastic. But also, it allowed the analysts to now actually see a more diverse and different outlook of different events in different ways. So we moved away from having one singular demand forecast to having dozens. So the analysts were able to now override or refine these forecasts in key situations where they knew machine learning models were actually performing better. So public holidays is a really big one, particularly when it comes to Christmas or New Year's Day. The analysts actually tend to look at what the machine learning models are doing more preferably ahead of what the linear models are doing, and they'll actually start overriding any actually market-facing models in response to that. Another key outlook here is now the ability to communicate and present a consensus of different forecasts. So it's a more diverse outlook, useful for situational awareness and preparedness. The idea of the consensus forecasts is that, when we have lots of different models that are trained and may have different objectives in different ways or different nuances to it, but once they're overlaid on each other, yes, that is pretty overwhelming. But there is a lot of uncertainty here. So when all the forecasts tend to say the same thing or have the same output, well, they're all kind of agreeing with each other. That's good. But when they all start disagreeing or deviating from each other, which usually happens at the peaks and the troughs, then it pretty much suggests that there is some degree of uncertainty that's manifesting itself under the hood somewhere, and something is being picked up in different ways by different models, and that's worth looking for. Now, it's not just about saying, yeah, we just need one really good model. The idea is that lots of different models are tailored in different ways and perform different things. In fact, there is just no one-size-fits-all approach. This graph, I'm not going to spend too long on it. All I have really here is a time of day, RMSE plot, just based on different regions. And we have two different models against each other. The only thing that I'm trying to show here is that based on the different times of day, based on the different regions, we get the zigzagging effect between the different models and their performance. So there isn't one model that is just always good. They're all very, very good. They're all very, very close to each other, very tight with their performance. But Some models work better than others. So actually having this whole consensus or this broad spectrum of different perspectives and outlooks is incredibly helpful for situational awareness and preparedness, and also helping more target the analysts of which key kind of models or key situations and other things to actually spend more time on. So boosted models, great. Machine learning models, fantastic. But there has been one limitation, is that boosted models cannot extrapolate. So what that means is that boosted models, XGBoost models and that kind of thing, they cannot actually forecast outside of what they saw during training, which means that if we're trying to get to a situation where we have a new extreme high or a peak or a new extreme low in our demand forecast, well, boosted models are pretty much useless for that. They're not reliable, and they're not going to be able to provide that information. So in order to reconcile with this, what we've been doing is focusing a lot more on deep learning and neural nets. So deep learning and neural networks, they are a really big leap forward for us. This is something that's still quite new. It's quite fresh. We have a few models that are implemented. Not going to lie, it took us a while to crack, but we did get there in the end. They have very intricate architecture. You can kind of think about it as, it's kind of modeled on the way that the brain kind of works. So if you get kind of new information, different neurons will start activating in order to produce a thought or an output. But what's great about this is that once we did crack it, we could see that we could get deep learning or neural networks that were, quite complex, quite sophisticated, but also that possessed really high accuracy. And no longer do we really have to compromise between this high accuracy and the ability to extrapolate or forecast truly novel situations. So some of the key benefits there is there are a lot of, deep learning is a big category. There's lots of different types of architectures there. There's a lot of specialized deep learning models, such as LSTM, which is long short-term memory, that are really great for sequential time series forecasting. They seem to remember previous sequences and previous observations and hold that in memory and use that to help forecast. So that's ideal for time series contexts. Deep learning models in general are just great performance across the board, really high accuracy, and they're able to actually extrapolate, which is really the thing that we were looking for. Lastly, and something that was quite surprising, is there wasn't a lot of feature extraction that was needed. A lot of it was quite automatic, depending on the kind of library and the way that we used it. So during the training process, there wasn't actually a lot of fuss. I want to give a case study of all of this in play. So this is South Australia, day ahead forecast. Let's dive into this. So this happened in December 21st, 22nd, just of last year. So this is during quite in the peak of our summer. So South Australia, we had our primary market-facing linear model forecasting for the next day and the day after that, 2 new record minimums. And yes, the graph is correct. Those are negative 200 plus forecasts that are coming out here. So when we have this much behind the meter DPV penetration, we are seeing these record mins happen all the time, and we are getting into negative territory pretty often in South Australia now. So that is quite technically the biggest generator in South Australia now is Beeple's behind the meter rooftop PV systems. So we have a linear model with, it's a pretty extreme day. We're forecasting 2 new mins back-to-back days. So the analysts want to see, okay, what are the machine learning models doing? What are they saying? Well, they're all bottoming out, right? Because machine learning models, they haven't seen anything below that kind of 0 megawatt kind of phase. So they weren't able to actually extrapolate beyond that minimum. So this kind of led the analysts in a bit of a scenario or situation where had they just been seeing the linear model is the only thing they could rely on, and the machine learning models were all of a sudden becoming a little bit irrelevant and unhelpful. But thankfully, we have these deep learning models that we had just developed just in time for our summer, and we had them predicting the troughs quite well. So the point here is that it's not necessarily just about accuracy. Just having models that can have different outlooks or a different diversity or saying something a little bit different to what our primary model is saying is incredibly useful in just understanding what the potential deviations and differences are. We have lots of probabilistic models, we have lots of different ensembles, we have lots of different ways that we're doing this, but this is just one primary way that we do that. So the fact that we have these deep learning models that are able to extrapolate, that are able to predict these troughs, that kind of say, hey, we are going to get a pretty low trough, maybe not as quite as low as the linear model is saying, was really useful. And it doesn't matter whether, well, it's not necessarily matter that, whether or not they're accurate, but I like this example because they absolutely nailed it. So they accurately predicted those troughs really well. There are some examples, where the deep learning models were a little bit off, but this was probably the biggest use case that we had the analysts actually relying and leaning on what the deep learning models were doing. So try to do that. So next frontier, embracing the black box with automated machine learning. So looking forward, well, actually right now we are actively working towards adopting auto ML solutions. So we are working with different things right now. We have some work that will probably wrap up by the end of this year. So hopefully if I'm invited back, I would love to present a little bit more on this topic. But the term black box, it can be a bit taboo. Some people might traditionally see it as negative, but really, at least from my perspective, I don't come from an energy background. I just care about getting the best forecast out there, right? So getting the best black box, that's a big part for me. So the goal here, it's not to replace human expertise, but it's to rapidly identify and deploy the best performing solutions for the given problems. It also will allow our data scientists to focus on higher level strategic challenges and model interpretation and less time actually building things out. So I really want to talk about kind of what this looks like in practice. So to do this, I'm going to talk about the model development lifecycle. So if anybody has actually done any machine learning or built models, it's pretty, stock standard process. First step, raw data extraction. So you get the data that you think is going to be useful. Next step, clean and consolidate them. As much as all this cool AI machine learning stuff is happening, this is 90% of the job. Everybody who's built a model knows that. But once we have our clean and consolidated model, we can get into our model development. Well, first step, feature engineering. So it's like, do we want to do interaction terms? Do we want to do rolling average? Do we want to do autoregressive information? There's just so many kind of different approaches and techniques that can be applied to this. Once you start doing all this manual feature engineering, next step, let's select our model. You want to do a linear model, a random forest, a deep learning model, whatever, pick one. After that, once you've selected the model, then it's time for hyperparameter tuning. Let's say it's a random forest. How many trees do you want to do? How low is the learning rate? How many leaves do you want to have there? So again, so many different combinations. You got to pick one. Once you do that, you can finally train your model. But that's just to get one model out of there. And you often don't want just one model. You probably want, lots of different models to compare to decide which is the same one. So you want to go all the way back to the beginning, and it becomes this reiterative process in which you are doing the feature engineering, you're selecting different models, you're doing different hyperparameter tuning steps. There can be so many combinations of permutations of different things that you want to do. It can become a very arduous process. Ultimately, the end is just to compare outcomes so you can select the final model, which you can then validate and deploy into production. But this is where automated machine learning has a bit of a benefit and upside. So the raw data extraction, the clean and consolidating data, that's not changing. I mean, as you being a data or subject matter expertise, you are still responsible for ensuring the quality of the data and the relevancy of that. But all of those steps in the middle that I was describing before, the model selection, the feature engineering, the hyperparameter tuning, I mean, technically everything that I just said can just be automated in one big engine. So all of that can be automated. You can kind of like let an engine run, feed it the data, sit back. Depending on the accuracy and the timing that you want, you can let it run for a few minutes. You can let it run for days if you don't really care about time. But the point is, it is purely an automated system. And at the end, you'll get lots of models, select the final one, validate and deploy. It's the same process, but incredibly more time efficient. And so some of the key benefits of this, ultimately, this is all to enable faster, easier build deployment of models. The other thing is that even though I keep talking black box, the reality is there is a ton of more comprehensive explainability tools available out there. So things like feature importance, Shapley tools, they're all a bit flawed, but they're all getting better. So there is starting to get a lot more transparency on more traditional black box models like machine learning, like deep learning. Another key benefit for this as well is it reduces the resources and barrier to entry. All of a sudden, model development and all of this like quite complex processes is no longer reserved for just data scientists. Really, anybody in our team who understands the data, who understands how to validate models and compare them, don't have to worry about the middle step of like, which model do I select? Which features do I have to put in? How do I do all the different hyperparameter tuning? That all becomes automated, so they can just really focus on making sure they set up the problem correctly with the right data and also compare and validate the correct one that is actually fit for purpose and valid. And the last point here is that it's incredibly scalable and adaptable to many use cases. If you've got the data and if you've got your objective, it's pretty much there. So I can see I'm out of time, so I'm not going to talk about this. Most of these slides were wall of text anyway, so I highly encourage people to just download if they're interested in it. Little things like, you know, advanced deep learning, transfer learning, reinforcement learning, which is actually the backbone of most large language models. Definitely not going to be talking about GraphCast because I think Sue and everyone gave such a good comprehensive of this, but ultimately, I just want to end with this, saying that our journey is one of continuous evolution. It's driven by the desire to leverage the most effective tools to provide the most accurate and insightful forecast for our market. So thank you.